Hi, welcome to this video. In this video, we're going to do a continuation of chemical equilibrium. Remember, on the previous video, we talked about so many things. We ended on the multiple equilibria of balanced equations. Now, in this video, as I will be continuing, I'll be starting with the effects of pressure, whereby we are going to talk about the relationship between the Kc and the Kp. Now, in this video, I will be elaborating more on the Kc and the Kp, and how do we know that this is a Kc, how do we know that this is a Kp. Now let us start. Now in this session, or in this lesson, like I said, we're going to talk about the Kc, we're going to talk about the relationship between the Kc and the Kp. But now, how do we get Kp and how do we get Kc? The expression that you see over here, it is an expression that we use to calculate equilibrium constant. How to calculate equilibrium constant, it depends on what it is provided to you at that time. You can determine the equilibrium constant in a form of Kp or in a form of Kc. If you calculate the equilibrium constant in a form of Kp, it's because you will be using your pressure. But now, if you calculate the equilibrium constant using Kc, it's because you will be using your concentration. Now, the expressions for Kp and Kc are the same, but they are different depending on the parameter that you will be using by that time. Now, because we want the relationship between the two constants using pressure and the concentration, we're going to derive these two formulae so that we can get into one formula that shows the relationship between the Kc and the Kp. So now, I don't like how they wrote it over here. Let us rewrite this expression of Kp. We know that Kp, it is denoted by this expression. Remember, we use pressure because we want to do expression of Kp using pressure. We're gonna say pressure of the reactants divided by pressure, the pressure of the products divided by pressure of the, remember this is Kc. We say, when we use concentration, we're gonna say concentration of the products divided by the concentration of the reactants. Now let's assume that we have chemical equation that says A maybe plus what? Plus B will be forming two molecules of C and D. Okay, let me write it in this way. Let me do it in this way so that we can have the coefficients. Okay, so let me erase it. So let me try it maybe in this way. So now let's say, for an example, we have our chemical equation to be A plus B to form AB, which is our product, right? Let's say this equation, it is reversible. Let's balance the equation. We have 1 mole of A, 1 mole of A. We have 2 on this side of the equation. That means you're going to need 2 to balance B. Now we affected A. That means on A, we're also going to need 2 over there. So now this is our chemical equation, right? So now to write the equilibrium expression for this equation, how are we going? Let's assume that all of these substances are in a gaseous molecule or are in an aqueous molecule, but let's assume they're in gaseous molecule. Remember, supposed to do it's better even if it's in a homogeneous equilibrium. So now the Kp is given by the pressure. We're using pressure of the products divided by pressure of the reactants. In this case, our pressure of AB, right? Pressure of AB at equilibrium will be to the power of 2 because we use the coefficients over there, divide by pressure of A at equilibrium, and then we use 2 over there. Remember, we are talking about the gases here, and then the pressure of B at equilibrium, its coefficient, its exponent over there, based on its coefficient is going to be 1. Okay, so this is how we write the I don't like it like this. I prefer to write it like this, but it's fine. You can also write it like that, because when it's written like this, it's more or less like a concentration. You get it? So now this is our Kp, or our equilibrium expression for this equation using the pressures, right? So now, because here we are talking about the gases, we know that law of ideal gas, it states that pressure multiplied by volume is equals to number of moles multiplied by R multiplied by T. But now, because here we are talking about the pressure, let us derive this equation to make pressure subject of the formula. So that means you're gonna have P is equals to number of moles multiplied by R multiplied by T over V. We divide both sides by V, and therefore our pressure in this case will be equals to, I'm just gonna isolate number of moles and volume aside, multiply by RT. We know that number of moles divide by volume, it is a concentration, right? I'm just gonna write a square bracket and say C to indicate it's a concentration, right? And over V, it's a molar concentration. We know that moles divide by volume units, could be in liters, mole per liter, or mole per cubic meter, whatever. It's your molar concentration multiplied by RT, and therefore this will be your pressure. So in this case, you can see that from the ideal gas law equation, we can determine the relationship between pressure and the concentration, right? If you increase concentration, pressure will thus also increase. So they are directly proportional. But remember, on this slide, we are talking about the relationship between Kc and Kp. We are not talking about the relationship between pressure and the concentration. Rather, we are talking about the relationship between the constants. So we're going to use this equation over here to substitute it over there, right? So now when you want to determine the pressure, you can use this expression over there. So now we're going to say Kp is equals to, now let us talk about the pressure of our product, which is AB. So how are you going to calculate it? We're going to substitute this concentration over there. We're going to say concentration of AB square brackets to the power of 2, right? Multiply by RT also to the power of 2. Divide by what is the pressure of A? Pressure of A, we're going to use the very same formula. So we're going to have A to the power of 2 multiply by RT to the power of 2. Therefore, what is the pressure of B? Again, we're using the very same formula. We're going to say concentration of B. Remember, it's B2 subscript over there, supposed to be 2. Multiply by RT, right? Now, Kp is equals to, I'm going to isolate the concentrations because here it's just simply multiplication. So that means I have AB to the power of 2 divide by concentration of A to the power of 2 multiply by concentration of B. And then multiply by, remember on top I have RT to the power of 2. Let me use my bracket. Divide by RT to the power of 2 multiply by RT. Now, from this expression, you can see that there is nothing major that I've just done. I just done my simple algebraic mathematical procedures, whereby I did my substitution onto this equation over here of equilibrium expression. I just substituted my pressure using this formula over there, just so that how did we manage to get onto this formula? Using ideal gas law equation, because we are talking about the gases. So that means this is how we can calculate a pressure using this. Now we managed to derive number of moles over V into concentration, and then we plugged it over there. So on top of here, we are talking about the pressure of the products. In this case, our product is AB. So this is what I did. I just did my substitutions whereby I use concentration instead of pressure. And therefore, now on this step, I isolated everything that you see at the bottom and on the above of this expression. So I just separated over here, it's multiplication. And now I can see here, it's what we have the equilibrium expression using concentrations. So now we know that this expression is given by Kc because we are now talking about the concentration. So here we have the Kc, and on this side of the equation we have the Kp, and therefore RT to the power of 2 will cancel RT to the power of 2. We're gonna left with only one RT, which is going to be RT to the power of, when I take it at the term's gonna be to the power of -1. Now you can see that in this equation, I managed to formulate KP and KC on the same equation. Now here we are talking about the relationship between the KC and the KP. I hope that was clear. Now on this slide over here, the very same equation, which is this equation, it is the same one that I have just showed you over here, how we derived it. Here, it was only about deriving it, whereby we use the KP from the get-go, and then we use the ideal gas equation, treated ideal gas equation, we substituted over there, and therefore we ended up to something that looks like this. But you can see over here, it's to the power of -1, could be any number over here. But now let us talk about this. So now this equation is the same as that one that we have just spoke about. So here on that previous slide, we got -1. I said that that -1 could be anything. It depends on the equation. So that -1, it is denoted by change in N. So change in N, we say it is the change in number of moles of your gaseous molecules on the reactant sides and on the product sides. So now, how to determine change in N? You're going to say moles of gaseous product minus moles of gaseous reactants, and you plug your value over there, and therefore you'll be able to determine your KP, or you'll be able to determine your KT, or whatever unknown that you will be asked to solve on this equation. Okay, so now here we can see the proper relationship between the KP and the KC. So now, here is how to calculate the concentration. We use this formula to calculate concentration, okay? Remember, when we calculate equilibrium constant, the substance, we use our substances in gaseous state or in aqueous state. So now, say for an example, your substances are not given in one of those states, they are given in liquids or they are given in solids. Now, how are we going to calculate their concentration? We're just going to use this formula where we're going to say density divided by molar mass of that substance, which is in liquid state or in solid state. And therefore, you will be able to determine your concentration of that substance using its density and the molar mass. We know how to calculate molar mass. We can use the periodic table. Okay, I hope that was clear. So now let us try to solve this question over here. This is an example of chemical equilibrium. Okay, they say to us, consider the following decomposition reaction. Okay, we are decomposing this reactant into these two products. And the most important thing that you need to do before you perform your calculations or whatever, make sure that you pay attention to the states of your substances. Gas. We are safe to plug everything on KC expression or KP expression. Number two, check whether your chemical equation it is balanced, because the coefficients are very important when writing your equilibrium expression. So is this chemical equation balanced? Because they didn't say consider your balance, they just say consider the following decomposition reaction. So it's your duty and your responsibility to make sure that your equation it is always balanced. Now, number of moles, we have 2 of nitrogen, 2, and balanced 7. 2 multiplied by 2 is going to be 4. And then, sorry, here we have 7. Let's go this side. 2 multiplied by 2 is going to be 4. This side is going to be 3 over 2 multiplied by 2 is going to be 3. And therefore, 3 plus 4 is going to be 7. And then oxygen, it is balanced. You see, it's very important to always recheck whether the equation is balanced. Now, after considering the decomposition of this reaction, what's happening? They say to us, assume that 30% decomposition from an initial pressure of 4,0 atm and calculate equilibrium constant. So this is Kp. Even if they say to you calculate the equilibrium constant, you need to understand that what is provided on the scenario or wherever we are provided with the pressure. That means our equilibrium constant, we're going to calculate it in using Kp expression in terms of pressure. But if we were only provided with the concentrations or the number of moles, we can determine our equilibrium constant using Kc. Okay, that's the first thing. That means we want to determine Kp, which is the same as Kc, just that we are using pressure over here. But you have to understand Kp and Kc are not the same, depending on this equation, the equation that we have just spoke about. Okay, depending on the equation that we have just spoke about, this equation over here. Okay, you can see that Kp is not the same as Kc, but in order for you to get Kp from Kc, you need temperature, number of moles, and ideal gas constant, just say. So now let us perform calculations over here. So they said 30% decomposition from initial pressure. Now, this is very important. When they say 30% decomposition, what does that mean? Let me show you before we can even do calculations. So how are we going to calculate Kp? We're going to use Rice table, or some they call it ICE. And there is this method that I call REREC. Okay, I use REREC most of the time when I'm provided with number of moles. That's why I use my REREC. But RICE, I use it most of the times when I'm provided with the pressure, and also when I'm provided with only concentrations. Okay, so let's use RICE. So our RICE, but let us start with our chemical equation first. Or I can do it like this, RICE. This is our ICE, or some they call it ICE. And then for R, some they call it reaction, but I call it ratio. Okay, call it ratio. And then here we have initial, everything initial. And then here we have change. Some, instead of them saying change, not to confuse this, some, instead of them saying change, they say reacted. Okay, this is reacted, actual, it's change. Okay, and then here we have equilibrium, everything at equilibrium. Equilibrium. And therefore now let us draw up a table based on the information provided to us. I'm sorry about my writing. So what matters is you see and you understand what is happening. So now, how many? 1, 2, 3. I'm gonna need 3 columns. Let's do it. So the first column, I'm just gonna write it over here. And then here we're gonna have the second column. Then this is the last column, right? And this will be the last column. Sorry about my writing and all of that. What matters, remember, is you understand. So now, therefore, here is our table. I try, right. So now, my chemical reaction, I'm gonna write it toward the top. That's what I do. Some I see they write it here and they say reaction is fine. You can do it however, as long as you do correct stuff. So I have N2O7 in gaseous state to produce 2NO2 in gaseous state plus 3/2O2 also in gaseous state. Okay, so let me change my color to perform calculations. So now let us start. This is the table that you need to know by yourself. Now here, wherever you see ratio, it is from the balanced chemical equation. I'm going to take the coefficients. What's the coefficient of this? It's 1. Coefficient of that is 2. And then coefficient of that one is 3/2. Right? This is the ratio of the chemical equation. And therefore, initial is everything provided to you initial. Let us go back to our statement and try to fish out for information. So they say to us, assume 30% decomposition from an initial pressure of, we have an initial pressure of 4,0 atmosphere. So meaning we are talking about the initial pressure of what? Of our reactant that is going, that it is going to be decomposed. So the initial pressure is going to be 4 atm. I mean, like, maybe someone would want to know, why am I not writing the initial pressure of NO2 and O2 as 4? Now, this is what is happening. This is what I want you to think about, okay? Each and every time when you perform these calculations, think about the graph, but we're going to do those graphs, don't worry, whereby this is initial. We are not disturbing equilibrium. we are starting the reaction. So from the beginning of the reaction, everything that is provided, it is the reactants. So we have the reactants over here, and then the product is 0. We have nothing for the products. So now remember, when the reactants interact with one another, their concentration or whatever, it decreases, but at the same time or simultaneously, the concentration or whatever of the products start to increase, and therefore there is a point, there is a time whereby these two, they're gonna reach equilibrium. Let's say maybe they reach equilibrium at this point. Well, let me just take it at the top. Sorry, let me just take it at the top. Let's say they reach equilibrium. Let me erase this not to confuse you, but you will see these graphs. We're gonna discuss them later on. Okay. So let's say now there is a time whereby these two now reaches equilibrium, right? Now, the reactants reaches equilibrium. This is the reactants, and this is the products, they reach equilibrium. So now, here's the thing. It's very important for you to know how to read these statements, okay? So now here, I'm gonna write 0, 0 for my product. Sometimes it depends. Sometimes we do not write 0, 0 here. It depends. If we disturb equilibrium from this position, obvious, if we disturb this equilibrium by factors, we know that the factors that affect chemical equilibrium is pressure, volume, concentration, and temperature, not catalyst. So if we disturb this equilibrium, obviously, initially, we have something there for products and the reactants, but something there for reactants will always be there. For example, here we have something. So this something is going to be used up while the products are being formed, and therefore we're going to reach the equilibrium. So because we are studying everything, we have nothing of the product, so we can't have pressure for the products. There is literally nothing, and so here it's 0. Okay, and therefore change is what reacted from this position to this position of before we reach of reaching equilibrium. This is the change. How many has reacted? That's why I say to you, some they say change, some they say it is reacted. So the reacted is from this position to that position. It's a difference. It's a difference. But now change for the products in this case is gonna be minus, and then change. Sorry, for the reactant, it's gonna be minus. For the products, it's gonna be positive. Positive again. Let me tell you why. Is because from here to here, what are you actually going to get? You are changing, right? You are changing from here to here. This is a change. And then it's a decrease from here to here. So your numerical value over there is supposed to be negative. We're gonna use minus instead, because we're gonna say minus subtract this, we're gonna get this at equilibrium. If you want to determine number of moles at this point, say this is x and this is y, and therefore this is change, you're gonna say change is equals to how much? So I don't want it like this. If you want to determine your x, say here it's your x. If you want to determine your x, you're gonna say change, right? You're gonna say initial, which is y. You're gonna say y subtract change, which is from this position. You can play with this if formula to determine x over there, this change over here. Okay, say 4, and then there you get 2. What is the change? You're gonna say 5 minus 2. It's how much? It's 3. That's the change, right? Initial moles from initial to equilibrium. It started with 5. Now at equilibrium, moles, it's 2. What's the change? It's 3. So how to determine number of moles at equilibrium? You're going to say initial number of moles, which is 5, subtract the change, which is 3. You're going to get 2. You see, you can play with it. That's why here on the right-hand side, we write negative. And this thing can also change. It can be positive here, it can be negative. That's why I'm saying it depends on what is happening. Know how to read your statements and know how to analyze your graphs. But you will see as time goes by, we're going to do different problems. So now here change, in this case, it's now let's talk about this. They said assume 30% decomposition from initial pressure. So this thing is the only one that decomposes, or it is the only one that is reacting, or it is the only one that is changing. So you can say reacted, change, or decomposition. So they said only 30% of this initial it has decomposed, so it has changed. So that means 30% of, we're going to determine 30% of initial pressure, which is 4. In this case, 30%, which is the 30% of initial pressure on my calculator, 0.3. I'm going to say 0.3 multiplied by 4, and then I get 1.2. So that means the composition is 1.2 atmosphere. It decreases, which is true, from 4 to 2. You see? So it's a change. So not decrease, you'll see a equilibrium. This is the equilibrium. And therefore now, how to calculate pressure at equilibrium? We're gonna say 4 subtract 1.2, and then we're gonna get how much? 2.8. We're gonna get 2.8. When you say 4 subtract 1.2, we get 2.8 at equilibrium. But we need these equilibriums as well so that we can determine Kp. So how are we going to get this? Firstly, we're going to need to know these two. How are you going to know these two? Now, each and every time when it gets to this step, okay, I call it RC ratio. I call it RC ratio. So RC ratio, I'm going to say ratio, I'm going to use my ratio. Here, I have 1, right, which is N207. I have 1 is 2. Here, I have 1.2, right? Now, because I'm looking for this, I can call it X. I'm looking for my X. It's my ratio. I'm going to align it on the line of the ratios. Is 2 over there. So I made a mistake. 2 supposed to come this side. Ratio supposed to be aligned at the same side, right? On the same side. So my ratio over here, remember this is 1, 1, and the ratio there is 2. And therefore this side is my X, which is what I'm looking for. Therefore I cross multiply 1 multiplied by X, it's X is equals to this multiplied by that. I'm going to say 1.2 on my calculator times 2, I get 2.4. So that means my X over here is 2.4. So that means this X over here is going to be 2.4. Therefore, 0 plus 2.4 is 2.4. Now I managed to get my pressure at equilibrium of NO2. I need this one then. How am I going to get this? I'm going to repeat the same thing. You can use this or you can use that. Let me use this. So my ratio is 1 is to, remember, 1.2. For this one, which is what I'm looking for, I'll call it Y, right? So I'm going to say my ratio there is 3 over 2 is to Y, which is what I'm looking for. Therefore, I'm cross multiplying 1 multiplied by Y, it's going to be Y. And then 3 over 2 multiplied by 2, it's going to be 3 atmosphere. So that means pressure over here, it's going to be 3 atmosphere, right? Is it 3? No. It's going to be, let me see, my ratio over here is 3 over 2, 3 over 2, 1, 1.2. Oh, it's 1.2, not 2. It's 1.2 here. We are multiplying by 1.2. Let's do it on our calculator. It's going to be 3 over 2 multiplied by 1.2 is, it's 1.8. Therefore, we get 1.8. That means our pressure, change in pressure over changed pressure, it's going to be 1.8, right? And therefore 0 plus 1.8 is going to be 1.8. And therefore now we have our pressure of our molecules or our gases at equilibrium. Therefore we can now calculate the equilibrium constant using the pressure. Remember we said it's Kp. Therefore now let us do our calculation. Let me change my color over here. Let me go to red. So we're going to say Kp is equals to, start with the expression first before you do your substitutions. So you're going to say pressure of the product, in this case, it's NO2, raise it to the power of 2 at equilibrium. Pressure of oxygen gas, which is given by 3 over 2, remember, from the balanced chemical equation, at equilibrium. Divide by pressure of the reactant. In this case, our reactant is this one, right? It's going to be N2 0.07 to the power of 1 equilibrium. Therefore, let us do substitutions. What is the pressure at equilibrium of NO2? In this case, we're going to have 2,4 to the power of, to the power of 2 multiplied by, what is the pressure of oxygen at equilibrium? It's 1,8 to the power of 3 over 2 divided by, what is the pressure of N307, N207 at equilibrium? That's simply 2,8 to the power of 1. Now, let us punch this on our calculator then to get the final answer. Now we're going to say 2,4 to the power of 2 multiplied by 1,8 to the power of 3 over 2 divided by 2,8. We get, if I do correct substitutions, let's see, we get on my calculator to 1 decimal place, we get 5. Get 5, doesn't have units, it's a constant, so we get 5. If I try to round it off to 2 decimal place or 1 decimal place, we get 5. Okay, all right, so now this is how we deal with this question over here. Let's have a look at this example over here once more again. They say to us, calculate the equilibrium amounts. They don't want Kp or Kc. They don't want equilibrium constant. They just want equilibrium amounts, right? If you start with 1 mole of PCl5 and end up with 0,135 mole of PCl3, and then this is the chemical equation. You see, for a fact that you do not need the states, okay? You do not need gas, liquid, aqueous, or solid. You do not need that because we just want to calculate the equilibrium amounts. But it is very important for this question to be presented with their states if we are going to calculate equilibrium constant. So we do not need equilibrium constant because we know that when we want to calculate equilibrium constant, we use aqueous or gases. Okay, so it's fine like this. The most important thing, again, you need to check whether the equation is balanced. P1, 1, Cl5, 3 plus 2 is 5. Everything, it is balanced. So remember, you need to know your table. Like I said, use your rice table, or some they call it ICE. I can use my REREC, but I'll use REREC, I think, on the next upcoming example. So now let us stick on the rice for now. Okay, so now remember, we're gonna do our rice table. Rice, for some, like I said, they call it ice. Okay, remember here it's ratio or reaction, some they say initial, and then here we have change, or we have decomposition, or we have reacted, and then here we have equilibrium. So now let us draw up our table. Okay, once more again, let's draw up our table over there. How many columns do we need? 3. Okay, we're gonna need 3. We're gonna need 3. We enlarge. Okay, so we have 1, we have 2, and the last one, last one, and then here's the last one, right? Here's our table, right? So remember our chemical reaction, we have PCl5 forming PCl3 plus Cl2. Then let me change my color pen. Remember, we want everything at equilibrium. We want everything here. This is our final answer right here, over here. So our ratio, remember, from the balanced chemical equation, is going to be 1 coefficient, 1 coefficient, 1 coefficient. See? And therefore, they say calculate equilibrium amounts. If you start, this is initial, most definitely. If you start with 1 mole of PCl5, which is your reactant. That means here we have 1 mole. Just gonna represent it in this way. 1 mole of PCl5. Because you are studying, you haven't formed the products yet. So that means, like, think of that table that I've just showed you over there. Here we're gonna have 0, 0, 0, and then here we're gonna have 0, 0, 0. And then on change, because we are starting on the reactant side, it's gonna be negative, and then the product side is gonna be positive. I say this can change. As much as this cannot always be 0 over here, you will see, okay? I'll explain that as time goes by, but I tried to explain on the previous example. And therefore, remember, and then you end up with 0,135 mole of PCl3. This is PCl3. You end up with this. You end up with this, it means at equilibrium, okay? You end up with 0,135 of PCl3. You end up with 0,135, right? So now we need equilibrium for this, we need equilibrium for that. But to get equilibrium for this, we need this so that we can say 1 subtract this, we get that. Same applies to here, we're gonna have to say this plus this, we get that. So this is easy. That means we're gonna have to determine this so that we can use our RC ratio, okay? So that we can use our RC ratio. So that means 0 plus it's this. So for the fact that you are adding to 0, that means you might as well, you can say this plus 0. This plus x supposed to get 0. It's the same as how much? It's the same as what? 0,135. Now let us use RC ratio to determine the others. For the fact that we have 1, 1, that means this, it is going to be the same. So that means here we also have 0,135. And then for the fact that we have 1, 1, that means this is going to be the same, which is going to be 0,135. Now let us determine here. We're going to say 1 subtract 0,135. How much do we get? We get 0,865. Same applies to here. We're going to say this plus that. It's going to be 0,135. And therefore, this is our final answer. Calculate the equilibrium amounts if this is true. So we don't need to calculate Kp or Kc. Number one, we do not know the states of our substances. So we do not know which one to include, which one to exclude. You see? So this is the final answer for this example.